The R-squared statistic helps us to know how accurate our model is. And it does that by describing how much of the variation or change in Y can be explained by the variable or variables in the model. So we're going to start out by talking about just one variable in the model for now. We're just going to talk about X being the only predictor variable that we use, and Y, of course, is the outcome. And by convention, X is the cause variable and Y is the outcome variable. So that's how we approach this, and that's how all the math is set up, so that's how we want to do it. Remember, you can only ever have one Y at a time, only one dependent variable, but later we're going to see that you can have multiple X variables in the same model, and all these same principles apply when you have multiple X variables. But we're going to start with just one X variable. And again, what we're trying to do is figure out how accurate our model is. Now, when we talk about a model in a regression model, what we're really talking about is the regression line that we've drawn, especially when we're only talking about two variables. When we have a single independent variable, we're just talking about a line. And we want to know how accurately that line predicts our real data. So I have two different images here that have really similar lines. They're on the same kind of plot. But one of them, you'll see that the data that we started with was more spread out from the line. And with the other one, the data is actually much closer to the line. So an R-squared value is going to measure the error in the Y direction. Because again, what we're trying to do is predict our outcome. That's what matters to us, is our outcome. And we're trying to use the cause variables to predict or describe or explain what's going on with Y. So we want to do a good job of accurately representing Y. So in this model up here, when I have a value of X and I plot that value in reality, like the real data point, these little green data points, and I plot the actual outcome with the actual cause, I get these green dots, and when I draw the estimated line, the regression line, that line is going to be a pretty accurate estimate of your actual data, right? Because the error is going to be small in that case. So this is something that we would expect to have a high R-squared. Now, when I say a high R-squared, I mean an R-squared that is approaching 1. 1 is the biggest value you can have. Because 1 is equal to 100%. You can interpret these as a percent of the variation explained. Not just any variation, the variation in Y. So the percent of variation or change in Y that's being explained by X, or your X variables if you have more than one of them, that's what your R-squared is telling you. So the closer to 1 or the closer to 100%, the better. It means you're doing a better job of predicting the change in Y. And you can see here that if I just have this X variable, I'm actually doing a pretty good job of predicting with high accuracy what our actual data points are going to be. That doesn't mean the data points are actually on the line, it just means they're closer to that line and our predictions are going to be more accurate. On this side, we would expect a lower R-squared. I'm just going to put lower R-squared, because we've explained less of the variation in Y. In other words, there's a lot of movement in Y in this vertical direction that's going on, and we're not necessarily doing a good job of predicting it all the time. So we're going to plug in our X values and our Y values, but you can see there's a lot of error between the line and the points. Because there's a lot of error in that space, that means we're doing a less good job of predicting the variation or change in that Y direction. Because we're predicting less of that, the R-squared will be closer to 0, right? So it ranges from 0 to 1. 0 is, we've explained, nothing. And higher values on their way to 1 indicate that we've explained more of the change in Y based on X. Our model is then X, or the set of X variables that we're using to explain or predict Y. And R-squared is a measure of the full model. So I've shown here a simple regression, which means we have only one explanatory variable, one independent variable to explain our dependent variable. But if we had more variables that we were using as cause variables or control variables, the R squared captures the entire model. So the sum of all of those gets stuck into that R squared value. So another visual that I like to use to explain that is a circle. So if you imagine that this circle is all of the variation in Y. So if we could fill in this whole circle with variables, we would perfectly predict Y. We'd have an R squared of 1, which is perfect prediction, okay? So what we're gonna do is we're gonna plug in our X variable here. And if our X variable explains only a little bit of the variation in Y, we'll have a small R squared. And if our X variable explains a lot of the variation in Y, we'll have a high R squared, closer to 1. The reason that I like this circle model is because it allows us to start talking about what happens if you include other variables in the model. So imagine that instead of a single X variable, you have several variables. Maybe these are other causes that you think might be causing Y, or maybe these are control variables that you're including just to see if they correlate with both X and Y, and therefore are important for making sure that you have a good causal argument. So we'll start with an X variable. And maybe we have a couple of different X variables and they're totally independent of each other and they're unrelated to each other. If you include both of those in the model, your R squared will increase by sort of the sum of the variation that's explained by each of these two variables. But sometimes what happens is you add in variables that share some of their explanatory power. So you might have other variables that you include that sort of take over part of that variation. And you can see that this shaded part here is overlap between these circles. So just because you have 3 variables doesn't mean your R squared always jumps up by the same amount, because sometimes there's shared variation there, and so your R squared won't go up quite as much. The other thing that this helps us understand is that when we include control variables, part of what we're trying to do, so here's our X variable, part of what we're trying to do is see if there's something, remember this is our variation in Y, this is how much of Y is being explained by X. If I include a control variable where the control variable is really the reason that we're seeing a correlation between X and Y, it'll actually make it so that we no longer see the variation due to X in the model. It's really cool. Multicollinearity is one of the ways that we see this, and we kind of play with that a little bit in our models and make sure that we've got just the right control variables and just the right independent variables to make sure that our R squared is clear, to make sure that our predictions are effective, and to make sure that we understand how to interpret those models. So we can talk about that more later. For now, I just want to introduce the idea that X is going to explain some amount of the variation in Y. It's going to be a function of other variables too, if you have other variables in the model. But if you have a simple regression model, X, the amount of Y that is explained by X, is going to be the size of your R squared. So this is a smaller R squared. If we had more variation explained by X, it would be a larger R squared. R squared again ranges between 0 and 1. So higher R squared means that we have higher accuracy when we're making predictions. It also means that we've explained more of the variation in Y, or more of the change in that vertical direction. What you're going to look for in your output for this, the way that you find this when you run your model in R and you call out the summary command so that you can get the output from your model, is you're going to look for the part of the output that says multiple R squared. And there's going to be a value there that ranges between 0 and 1. That's going to be your R squared value. People ask me all the time, what's a good R squared? Like, what R squared am I shooting for, right? And that is not a great way to think about this, because it completely depends on your context. It depends on the question you're asking. It depends on the kind of data that you're working with. There are some circumstances where like a 90% R squared, like a 0.9 R squared is going to be like amazing and incredible that you were able to explain that much of the variation in Y. And other circumstances when that is a terrible model and you're like, why would you ever make decisions based on a model that only has 90% accuracy? So it totally depends on the kind of phenomenon that you're trying to predict. In general though, it also depends on what the question type is that you're asking. So the most important use for an R squared is in figuring out the accuracy of the overall model. So if you're trying to run a type 3 question where all you're trying to do is do a good job of predicting Y, your whole goal, like you don't actually care about like slope coefficients or the relationships between the X and the Y, none of that. You don't have to look at any of those statistics, because what you really care about, if all you're trying to do is predict Y, what you're looking for is a high R squared. And you're going to judge your entire model by whether or not you have variables that you can use in the future for predictions and you get a high R squared. So this is going to be your entire focus with a type 3 model. Now, if you're doing a type 1 model or a type 2 where you're looking at the correlation between X and Y, and that's really your big question, like does X cause Y? So question type 1, a single cause question where you're like, does X cause Y? In that case, the R squared, the only thing that the R squared tells you is how much of Y is being predicted by X. And you might run a simple model like this with just those two variables and figure out how much of Y is being predicted by X alone. After that, you're going to include other variables in the model to rule out the possibility that X is not actually the cause of Y, but really both of them correlate with some other Z variables. So that's where you end up like this. And you may end up with a higher R squared in these models when you're including your control variables in there, but that doesn't tell you anything, especially if you discover that X no longer has a correlation with Y, because that was your question, does X correlate with Y? And the reason you're including the Z variables isn't to make the whole model more predictive of Y. The reason you're including them is to rule them out as the reason X appears to correlate with Y. So in a model like that, you're not actually all that interested in R squared, except maybe a little bit when you're doing the simple regression. Instead, what you're going to look for in a model like that is you're going to look at your beta, your slope coefficient, and your p-value, and you're going to try to figure that out. Somewhere in between those two things is the question type 2. Question type 2 is when you are looking at more than one cause. So when you're looking at more than one cause, part of what you're trying to ask is not just do they correlate and how much and in what direction, but you're also trying to ask how much impact do they have on Y. So in a type 2 question where you're saying which has the greater impact on Y, is it X1 or is it X2? Then you might start looking at your R squared. You'll run one model with your X1 and one model with your X2, and you're going to see which of those two has the higher R squared, because that's going to tell you which has the bigger impact. And that would again look something like this. And in this example that I'm drawing, X2 would have a bigger impact. So if I ran just a model with X2, I'd have a higher R squared than if I ran a model with just X1. And that is useful information. That tells us something. And in that case, it's kind of a hybrid between the single cause where we're just interested in the correlation and the predictive model where we're just interested in predicting Y. With that question type 2, we're interested in which cause has the biggest impact on predicting Y. So it's kind of a hybrid, and the R squared is really useful there. I think that's it for right now, but these are really cool statistics, and in combination, the R squared and the slope coefficients can tell you a lot about the world, and you can run a lot of different models. And once you think about the ways that those models fit together and what the R squared changes and the changes in the slope coefficients, what all that is doing, it can really help you to start to put together a good picture of what's happening in reality and how to make good decisions based on it.